Good afternoon. Great to see you all over here, and hope you're having a great reInvent so far. Welcome to CMP320. This is our compute breakout session where you're going to learn more about how Graviton enables the best price performance for your workloads. I'm Sudhir Raman. I lead product management for EC2 core compute products here at AWS. And co-presenting with me today are Ali Saidi, Senior Principal Engineer at AWS, and our featured customer speaker from Robinhood Markets, Sujit Katakam. Over the next hour or so, we're going to be exploring how Graviton enables the best price performance. We're going to talk more about work performance, discuss customer stories, and then talk through how you can best transition your workloads to Graviton. We're also going to hear from Sujit around how Robinhood adopted Graviton, their entire journey, and the key takeaways and learnings from their adoption journey. So with that, let's get started. AWS has been investing in building custom chips over the last several years, and these have spanned multiple areas across data center infrastructure, core compute, as well as machine learning. The AWS Nitro system that's been powering our EC2 instance types since late 2017 consists of custom Nitro cards or custom chips that allow us to offload storage and networking of the main processor and maximize resource efficiency. In Inferentia and Trainium, we have custom chips that are designed to accelerate machine learning, deep learning, as well as generative AI applications. And then we have Graviton, which is our general purpose chip for modern servers, targeted at delivering the best price performance for nearly every workload in the cloud. And before we go deeper into Graviton, let's spend a minute talking about why AWS has embarked on the journey of building custom chips. And there are many reasons for this, starting with specialization. This allows us to bring in the right feature set, optimize for our use cases in the cloud, and optimize for cost and power. Speed. From defining the product to building the servers to landing those in our data centers, all the teams that own both the hardware and the software stack are under one roof. Innovation, where we are able to create disruptive value for customers by innovating across the stack, from the CPU to the server to the infrastructure to the virtualization layer, all the way to the application layer, and doing all of that holistically as opposed to doing that in a silo. And finally, security, where Nitro provides us with a way to enhance the security bar of our servers to a hardware-based root of trust mechanism. So our Graviton journey started back in 2018 with the first Graviton chip that proved that applications could run on ARM-based EC2 instances. And since then, with every generation, we pushed the performance, the capabilities, and the efficiency of these chips. And today, we are in our fourth generation of Graviton 4 processors that deliver the best price performance in EC2 for a variety of workloads. And today, we have over 150 Graviton chip-powered EC2 instances available globally. And by enhancing the capabilities, the performance, and the efficiency with each generation, what that does is that we've also been able to enhance the number of workloads that can benefit from the improvements in the performance and the cost benefits that are delivered by Graviton. So this includes everything from application and gaming servers, through media encoding, through high-performance computing, all the way to large databases, analytics, and CPU-based machine learning applications. Let's start taking a look at some of the generations. So starting with Graviton 2, we launched Graviton 2 in 2019 to deliver up to 40% better price performance over other comparable instances. And today we have 13 Graviton 2 instance types, covering workloads that are spanning compute, memory, general purpose, network, storage optimized, as well as GPU attached versions. Graviton 3 came 2 years later and continued to push the bar on the performance with respect to compute performance, delivering another 25% higher performance over Graviton 2, as well as delivering a 2x improvement in floating point performance over Graviton 2. Graviton 3 was also the first time that we brought DDR5 memory into our data centers, delivering up to 50% more bandwidth than DDR4 memory. We also see a lot of customers that are running AI and ML workloads on CPUs, and Graviton 3 brings a lot of architectural improvements targeted at their workloads. This includes doubling the vector width, support for bfloat 16 instructions. And when you combine that with some of the improvements in the ARM64 ecosystem for ML applications, customers can see up to a 3x improvement on AI ML applications when they run on Graviton 3 versus Graviton 2. And in terms of the portfolio of EC2 instance types, today we have 8 instance types that are powered by Graviton 3 chips that span compute, general purpose, memory, networking, and we also have an instance specially just for high-performance computing that delivers improved vector bandwidth that benefits those applications. Which now brings us to Graviton 4, which is the most powerful and the most energy-efficient chip that we've built thus far, and it's our latest generation. And each Graviton 4 chip has 50% more cores, twice the L2 cache, and 75% more bandwidth over Graviton 3. Not only that, Graviton 4 is also the first time we've supported multi-socket coherency, which means that we are now able to target larger scale-up workloads and address the most demanding databases as well as big data analytics. Let's take a look at some of the EC2 instances powered by Graviton 4. So over the last few months, we've started rolling out a bunch of different EC2 instances that are powered by Graviton 4 chips. And we already have our latest 8th generation compute, memory, and general purpose instances powered by Graviton 4. And each of these enable the best price performance in their instance families. They deliver up to 30% higher compute performance compared to Graviton 3. And they provide scale up in terms of 3x the number of vCPUs and memory, all the way up to 3 terabytes of DDR5 memory. All of them are built on the 5th generation Nitro system and are generally available today across several global regions. The latest addition to our Graviton 4 instance lineup is the I8G storage optimized instance that we just launched a couple of days ago at the start of re:Invent. I8G is great for latency-sensitive and I/O-sensitive storage applications like transactional databases and analytic workloads. And it delivers with 22.5 terabytes of local NVMe instance storage, up to 65% better real-time storage performance. Additionally, just yesterday, we also pre-announced a network-optimized Graviton 4 instance that delivers, that's based on our 6th generation Nitro system, and that's expected to be available in the coming weeks. Let's transition to customers. We're seeing a lot of customers adopt Graviton 4 for a variety of use cases. Let's take a look at some of these examples. Epic Games is a leading interactive entertainment company, and they operate Fortnite, which is one of the world's largest games. And when Epic Games used and tested Graviton 4, they found it to be the fastest instance that they've ever tested. IBM and IBM Instana Observability provides complete visibility over your application stack. And on top of the savings that they had already observed with Graviton 3, IBM found another 30% improvement in CPU utilization when they moved to Graviton 4. SAP last year announced that SAP HANA Cloud was live on Graviton instances. And now with Graviton 4, they are seeing another up to a 40% improvement in transactional workloads versus Graviton 3-based use cases. EDA, or electronic design automation, is a key workload category that is needed for designing, testing, verifying, and manufacturing of custom chips. And a lot of semiconductor companies, as well as AWS, use the cloud to run these EDA workloads. And what you see below here is a snapshot of a cluster that was used to support the development of the Graviton 4 chip itself. And what you see here is a cluster that's running at scale. It requires high-performance computing, and it has peaks almost 5x to normal usage. And by providing fast processing power, what we are enabling with Graviton 4 is the ability for many chip companies, as well as AWS, to bring some of these EDA workloads into the cloud and run that in the most efficient manner and improve time to market of those chips. For example, ARM, when they used the new Graviton 4-based X8G instance, for a formal verification workload, which is one of the EDR workloads, they saw up to a 50% improvement compared to the previous generation, which greatly accelerates their time to market. Now, in terms of customer momentum, we see customers across all categories, geographies, verticals, and all sizes adopting Graviton in a big way. And today, 95% of the top 1,000 EC2 customers are drawing on Graviton. That's not all. And this was just announced earlier at re:Invent. Over the last 2 years, more than 50% of new compute capacity that we've deployed is based on AWS Graviton. Now, in addition to price performance benefits, a lot of organizations today have a focus on sustainability and lowering carbon footprint. And with Graviton consuming up to 60% less energy to compute the same workload as other comparable processors, a number of customers are using Graviton to make progress towards their sustainability goals. Let's take a look at some examples. Pinterest. They use thousands of EC2 instances for their API stack. And when they moved that over to Graviton, they saw up to a 62% reduction in carbon emissions per API request. Zendesk, they've moved their core compute application over to Graviton, and they saw in addition to the performance improving by 30%, they saw up to a 50% reduction in monthly carbon emissions. And finally, Aerospike is optimized for Graviton processors, and according to their report, they've seen a 49% reduction in carbon emission. So with that, I would now like to transition over and invite Ali Saidi to dive deeper into the Graviton 4 processor.
Thank you, Sudhir. So let's dive into what Graviton 4 looks like. This is a picture of a Graviton 4 CPU die. With Graviton, we've been iterating at a consistent cadence, from Graviton 2 to Graviton 3 and now to Graviton 4. Graviton 4 increased the number of CPU cores per die by 50%, or per socket by 50%. We went from 64 to 96 cores. We also have a much bigger L2 cache in Graviton 4. And the reason for this is simple. We want to put as much cache as we can as close to that processor, because we've seen with big workloads, not with benchmarks, that they need a lot of cache. That's what we've done here. Just like Graviton 3, it's a 7-chiplet design with 1 central compute die, 4 DDR dies, and 2 PCI dies. The DDR dies are DDR5, and when it was launched, it was the fastest DDR system in EC2, with 12 channels of DDR5 5600 and up to 96 lanes, or 96 lanes, sorry, of PCIe. Let's look a little closer at what this looks like in the actual chip. All the cores are connected with a mesh, and there's portions of the last level cache that are scattered across that mesh as well. Those 12 channels of DDR provide over 500 gigabytes a second of theoretical bandwidth and just under 500 gigabytes a second of achievable bandwidth. And with Graviton, we've really been expanding the set of workloads that are applicable. We started with Graviton 1. It was really about just showing that you could have the same experience with an ARM processor as you could an x86 one. You could launch different AMIs, you could start and stop instances, you could attach and detach I/O devices, and some customers saw workloads that performed well there. But with Graviton 2, we started seeing applicability to scale-out workloads. We saw customers running Java and Go, Rust, key value stores, and load balancers. Graviton 3 expanded this further. With the increased SIMD width that Graviton 3 provided, we saw HPC and machine learning workloads start migrating to Graviton. And now with Graviton 4, we're talking about scale-up workloads. We had customers that came to us and said, we've moved all of our small databases to Graviton, but what we're looking for is to be able to move the big ones. We need 96 cores, or we need 192 cores databases. And that's what Graviton 4 is here to solve, to provide not only 30% improvement in performance for normal workloads, but also to be able to run your most demanding ones. One of the ways we do this is by scaling up. Graviton 4 is the first time where we support multi-socket coherence. So not only do we have 50% more cores per socket, but we can take 2 sockets and put them together into a single system to give you VMs of up to 192 cores, or 48x large. In addition to that, we have as much as 3x the DRAM capacity with our R8Gs, or with X8Gs up to twice that. So 3 terabytes of RAM and 192 cores in the largest instances. In addition to optimizing performance of real workloads, we've also been encrypting all the high-speed interfaces in Graviton. We started this with Graviton 2, where we were the first chip to encrypt the DRAM interface. But with Graviton 4, we've expanded this. We're now encrypting the interface between our Nitro cards and our Graviton chips, and also the chip-to-chip link I just talked about in the previous slide between Graviton chips are also encrypted. Just like we attest the boot of our Nitro cards, every Graviton 4 raises the bar in security by validating, monitoring, and protecting every stage of the host boot through an attestation process. With Graviton 3, we started by showing you a server that had 3 sockets, not just the normal 2. And the reason we could do that is we have a very close coupling between our Nitro cards and our hosts. With Graviton 4, we've increased that flexibility further. This dual socket server you see here can be 2 non-coherent virtual instances, or sets of virtual instances, 1 large coherent instance, 2 metal instances, or 1 big coherent metal instance. And we get to save power by turning off that coherence when we don't actually need it to offer those large 48XLs. When we developed Graviton 4, we paid close attention to real workloads, looking how they performed and collaborating with ARM on what the performance of the CPU should look like. So to help visualize this, we can use these radar graphs. A single plot gives us a holistic view on a workload's characteristics. Each axis corresponds to a different chip design trait, with the value corresponding to the workload sensitivity to that particular trait, and ultimately determining its overall performance. Processors can be thought of really as having 2 halves. There's the front end of it, which receives instructions, and its performance is influenced by factors like branches, the number of branch targets, the number of instructions that are being touched, and ultimately, these result in front-end stalls. The back half of the processor is what actually executes those instructions, and it's sensitive to properties like hitting in the L1, L2, and L3 cache, the instruction window size, and ultimately, these result in back-end stalls. And so if we plot a workload on these kinds of graphs and look at the left or the right, it lets us see at a glance, is this workload sensitive to the front end or to the back end? The higher the value, the more relative that is, and smaller is better. So what can these kinds of graphs teach us? Let's start with a benchmark. So for this traditional benchmark, we see it's stressing the L3 cache with a large number of back-end stalls. This tells us that the back end of the pipeline generally wasn't able to do a lot of work and to find work to do. And while we see those sensitivities on the right-hand side of the graph, we don't really see much on the left. And when you step back and think about it, this makes a ton of sense. Most benchmarks are small kernels that someone's extracted from a larger application, and you do things repetitively in a loop over and over again. So it doesn't really touch the front end of the processor very much. It just touches the back end a lot. They're meant to be stable and easy to run. Let's compare this to what some real workloads look like, workloads that we expect our customers to run, like Cassandra, Groovy, or Nginx. When you compare these, you see they look totally different. They're bottlenecked by a completely different set of factors. Particularly, the workloads don't care about the things as the micro benchmarks cared about, but they care about the left-hand side of the graph a lot more. The branch predictor, the TLB misses, the instruction side of the processor. Unlike these benchmarks, the front end is causing the stalling. So that led us to do some things. One interesting thing you can determine from that is workloads are a lot bigger than benchmarks, especially on that instruction side. That's one of the reasons why you made the L2 cache twice as large in Graviton 4. It was just fit more of the instructions for real workloads. With CPUs, we also have particular improvements to improve the front end of the CPU, particularly around branches and making the branch predictor a lot larger. And lastly, Graviton 4 supports the ARM v9 architecture that adds some new instructions, particularly around ROP and JOP mitigation, like branch target identification. Okay, so we talked a bit about behind the scenes, what does Graviton 4 look like? Let's talk a little bit about how does it perform. And I'm going to start here with MySQL, and I'll walk through a couple of workloads. In all these cases, I'm comparing a Graviton 3-based system, an R7G, to a Graviton 4-based system, an R8G. And in all these cases, we're also using just 8 vCPU VMs, so relatively small VMs. And here, I'm using HammerDB. HammerDB is an open source load generator. It's meant to mimic a company that keeps track of stock in warehouses, receives orders, processes payments, delivers orders, checks stock. And it measures performance in terms of the number of new orders per minute that can be processed in the database. And so going from Graviton 3 to Graviton 4, we see an amazing 40% increase in performance in one generation of processor. These numbers aren't necessarily unique. Here, I've got Nginx. Nginx is a popular web server. It can also be a load balancer. And in this configuration, it's being a load balancer. So we fixed a load generator, and we fixed the number of web servers. And in the middle, we either have an R7G or we have an R8G being a load balancer. And here, we have a 30% increase in performance. Similarly, Grails is an open source Java web application framework that uses Groovy, and Groovy itself runs on a JVM. And we found this to be more representative of typical Java workloads and Java stacks that our customers run. Here too, looking at a Graviton 3-based instance versus a Graviton 4 one, we see a 45% increase in requests per second. We've also been spending a lot of time on machine learning and machine learning frameworks and getting those to run on Graviton. Today, a large number of frameworks support running on Graviton. We've improved performance in PyTorch, going from PyTorch 1.13 to PyTorch 2 by over 3.5x in some models. With Torch to compile, we've seen a 2x improvement with PyTorch 3.21. We're working on improvements with JAX right now that gives a 1.5x improvement, and with other frameworks as well. In addition to those, going from Graviton 3 to Graviton 4, we typically see a 20 to 30% increase in performance as well. And if we step back and consider where we started back in 2018 with the A1 instance, where we got to in 2019 with Graviton 2, in 2021 with Graviton 3, and last year with Graviton 4, we can see around a 4x, depending on the workload, increase in performance. It's just a huge number for 4 generations. So overall, with Graviton, we've got industry-leading performance, up to 30% higher performance than Graviton 3. The first system in our cloud that had DDR5 5600 memory, the best price performance in EC2, and as much as 3x larger instances than Graviton 3. So I'm going to now hand it over to Sujith to talk about how Robinhood adopted Graviton.
Hello, everyone. I'm Sujith from Robinhood. I'm currently working as a staff software engineer, and I'm going to walk you through about how Robinhood took upon the journey of Graviton and why we chose Graviton in the first place. I'm highly confident that there is something for everyone here to take away and embed into your migration strategy if you're looking to move to Graviton. Before I dive into Graviton or compute in general, let me introduce who Robinhood is. If you're not familiar, Robinhood's mission is to democratize finance for all. As part of this mission, Robinhood has released several products ranging from stock trading to buying and selling crypto to credit card and much more. Millions of customers use Robinhood on a daily basis, and it's very important for our infrastructure to be cost effective, highly performant, and scalable so that we can pursue our growth and innovation as we do day in and day out. Before I talk about why we chose Graviton, let me introduce the compute at Robinhood and give you an idea of how it looks like. We primarily use Kubernetes as our primary means of compute, and it is backed by AWS EC2 instances. And services at Robinhood kind of fall into one of these categories, ranging from like the edge that is exposed to the user, API, server, and platform services, and the data stores. As you can see, we have a diverse set of workloads, which can be ranging from being memory intensive, or CPU intensive, or disk I/O intensive, and we wanted to make sure that the new architecture that we introduce is compatible and can work with all these kinds of workloads. So we have to be very thorough and cognizant on choosing the right architecture for them. Because we want to make sure the whole transition to the new architecture benefits all the different kinds of workloads, not just a subset of them. All right, why did we choose Graviton? There are primarily 4 reasons why we chose Graviton. As talked about by the other presenters, it's on the edge of innovation. Like every generation is significantly better than the previous generation. So we wanted to jump ahead of the curve and be part of this journey so that we can yield all the benefits that Graviton has to offer. Secondly, the price per CPU core, like Graviton, is generally a little less expensive compared to the Intel family or AMD family of instance types. So given we run several thousands of EC2 instances in our production clusters, every bit of price efficiency helps us. And the third one is more around the sustainability goals. Like Robinhood publishes its ESG numbers publicly, and we believe that moving to Graviton will accelerate us in the ESG journey to be able to be more sustainable. And as you have seen, as described by Ali, it is very efficient in terms of like the resource utilization. So we wanted to get an idea of like what it means to run and apply Graviton to Robinhood workloads and see for ourselves if we can claim the wins around the resource utilization as well. So the meat of the presentation is going to talk about how we have gone through the journey of adopting Graviton, what are the different phases that we went through, and talk about like some of the challenges and what did we implement to make sure Graviton is a primary compute type for us. On a very high level, our journey to Graviton started in June of 2022. This is right around the time when Graviton 3 has become very popular. And we kind of started with a simple POC to really understand if it benefits Robinhood to move to Graviton. And after that, we never looked back. We went on to migrating 90% plus of our production workloads to Graviton, roughly in the time frame of 18 to 20 months. Okay, let's talk about the different phases so that I can give you more details. For the first phase was the POC phase, where we wanted to see for ourselves, as I mentioned before. So the 3 things that we were looking for from the POC were trying to understand what it means to build and release ARM64 compatible artifacts. Also try to understand if our systems are able to support ARM64 as is, or if we need to make any changes to our OS, or do we have to upgrade any Python packages or any processes along the way to make sure that we are able to release ARM64 and use them in our stack. And lastly, we wanted to see like how do the benchmarking ourselves to see if the performance is as expected and if it's working as expected and giving us the benefits that we were looking for. And I think it's easy to say that the POC was successful because we are talking about the additional phases that we went through. So the POC was a great success. So we went on to like adding ARM64 support in our SDLC cycle. There are three main areas where we had to make sure the ARM64 architecture was supported. It's in the build, release, and the deploy phases. Let's dive into the build phase. To set the stage, Robinhood has a lot of compiled code, even though we use Golang. There are certain dependencies that use native languages like C, C++, or Rust. In addition to that, we do have a lot of services that are on Python, and they do have certain packages in native code as well. So we have to make sure that all of these can compile and be executable on the ARM64 architecture. As you can see here, we use Bazel as the primary means. And for Golang, it was quite easy because Golang supports cross-compilation by default. So we did not have to do much to enable Golang services to be able to run on Graviton. But for Python, as you can see, the Python process itself is a little slow because we have to make sure that we pip install the packages. If they are pre-installed, we just pull them from Artifactory, but otherwise we have to make sure we compile the code using the C compiler and make sure that this artifact is released. The process in general is slow, but especially when you're trying to run this, perform the same process for ARM64 architecture, it gets even further slower because we were using AMD instances to be able to compile the code for ARM64. So in order to overcome this challenge, we made certain improvements. The primary improvement we made was we overhauled the C toolchain that is used in our Bazel workflow to be able to cross-compile. That means it was able to compile the same code for multiple architectures using the same toolchain. This enabled us to kind of release the artifacts for multiple architectures. The second thing was like for Python services, as we had to kind of compile the code, we kind of front-loaded the work by pre-building the Python wheels and uploading them to Artifactory. That means in the process of releasing the artifact, it was much, much faster. And the third one was we kind of made sure that we used ARM64 build agents to build the ARM64 images. This made sure that we don't have to use virtualization and emulation. So the entire process was much, much smoother. And lastly, we released multi-architecture based images for all of our applications to leverage. This means that if we were to roll back to AMD 64 during the migration process, it's always possible, and the adoption was much, much safer. All right, let's talk about the release phase. In the release phase, as mentioned before, we use Bazel. So in the release pipeline, we had to make some adjustments where we were running the tests on both architectures. Again, this is to make sure that if you were to roll back, the rollback was very straightforward and doesn't involve taking any additional risk of not testing the code on AMD 64. Once we have tested the code and it is eligible to be released, we made sure that we released both AMD and ARM64 images. And we push the relevant artifacts to S3 and AWS ECR. But if we release two different artifacts, one for AMD and one for ARM64, how do we make sure that the Kubernetes ecosystem pulls the right artifact whenever we are trying to deploy the workload? In order to kind of make this much, much simpler, we released multi-architecture AWS ECR image indexes. The image indexes basically are pointers to two different images. One is AMD, one is ARM64. And the container runtime on the Kubernetes nodes is capable enough on detecting the architecture of the node and pulling the right image from the index itself. And we also made sure that there is a new user-facing API that is exposed. That means the migration is an easier option and very transparent to the users without having to know the internals about what kind of packages they're using, like what it means to be pre-building the packages. All of this is taken care of by this API. And lastly, obviously, AWS ECR has certain quotas for how many images a particular repo can have. As we have doubled the number of images that we were releasing, we had to make sure that we don't exhaust the limit at any point. So we kind of added some robust ECR repo policies to make sure all the latest and the deployable tags are always available. And also we built a in-house cleaner job that can recognize already deployed tags as well as the latest, say, 1,000 tags and retain them while kind of deprecating the old ones. All right, let's talk about the deploy phase. I think as I have already set the stage, we use Kubernetes as our compute platform. And Kubernetes cluster and the cluster management tool we use, namely kops, already supports ARM64. So from a compute standpoint, that was already taken care of. But we have to make sure that the container runtime is architecture aware. That means it can pull the right image from the image index. So we did some tests, and we were successful with whatever Docker and any other container runtime that we use are capable of doing this. And once we have verified that there is less work for us to do, we relied on like the out-of-the-box features that the container runtime provided. And lastly, as you have seen through the adoption phase, we wanted it to be an opt-in rather than enforcement. So we built a workflow for opt-in by creating another compute layer API by exposing certain taints and tolerations. Our Kubernetes clusters use autoscaling groups behind the scenes. So what we did was we created dedicated ASGs for Graviton, and we kind of deployed the workloads on these dedicated ASGs so that the process is fungible and the rollback is much, much straightforward. As with any software, there is always a risk that things will go wrong, and things do go wrong. So we wanted to be very proactive in terms of adding certain guardrails on preventing things from going haywire. So the first check that we added was adding some admission checks. Primarily what the admission checks are around is looking to see if the artifact being deployed on Graviton is indeed compatible. And if it is indeed using image indexes, because we always wanted a path to roll back. And we also wanted to make sure that the application is already releasing the artifacts and using the right affinity to be eligible to be deployed on these Graviton ASGs. If any of the prerequisites failed, we administratively routed them back to x86 so that the application's reliability and uptime is not impacted. The second guardrail we added was around like using AWS's concept of mixed instance policies. So mixed instance policies allow you to have a sorted stack ranked list of preferred instance types. So we kind of wanted to create multi-arch ASGs because Graviton 3 was a relatively newer instance type, and we wanted to make sure that we don't run into any instance fill rate concerns. So what we did was we kind of introduced this concept of multi-architecture by making sure the fallback instance types in this autoscaling group are pointing to x86. So in case when we try to launch an instance and we cannot find, AWS cannot find a Graviton instance, it will go through the sorted list of instance types that we have preferred. And one of them is x86, which we have been running for several years. So we are confident that from an instance launch perspective, there is never a risk of business continuity. I want to extend huge kudos to AWS here. We added an alert to detect if an x86 instance is ever launched, but this alert never fired in the last 2 years. So it's awesome to see that. All right, now that we have done the POC, we have added ARM64 support, and we exposed a bunch of APIs. We went through the process of adopting Graviton, for all our workloads. So there is a simple strategy that we used. One is prefer Golang because it was automatically eligible and we didn't have to do anything to adopt the applications onto Graviton while we build the support for pre-built Python wheels and packages. The second part of the strategy is to kind of sort by impact. So like from a migration standpoint, we wanted to front load finding the biggest blockers by taking on some complex services. This way we solve the problem for one. That means we solve the problem for a bulk of our workloads. And the second part of the impact is primarily around the footprint. So we try to prioritize applications which have the largest footprint. This way we kind of yield the gains much earlier in the process. Okay, so now this is the checklist for the migration. It's very simple. So first what we do is we expect the application workload to use the API to release multi-architecture artifacts. And whatever admission checks that we were performing at the Kubernetes layer, we expose through a ad hoc compatibility check tool that can perform the same checks and provide shift left guarantees that the application is indeed eligible. So this enabled for faster iteration in case an application is not compatible. It can be caught very early in the process rather than having to go through all the steps in the migration process. Once the compatibility is verified, all the users have to do is opt into this multi-architecture compute by using the compute API that we have exposed. And once this configuration has been merged, you just deploy your latest configurations and voila, you are running on Graviton. All right, the most important piece. Now, Graviton says that it's very cost efficient. The resource utilization is much more minimal, and it is supposed to be helping us reduce the resource requests from all our applications. So the workflow is pretty straightforward. We monitor the resource utilization for several days, and we try to kind of slowly decrement the resource requests so that the used to requested ratio of resources is in a ballpark that we are comfortable with. So the whole process was repeated until we reach a place where we are comfortable with the ratio, and that way we were able to kind of reduce the resources requested by the workloads and bin pack them onto the Kubernetes EC2 nodes, thereby shrinking the capacity of the Kubernetes cluster. So we are not done with realizing gains. There is a lot more to be done, especially with Graviton 4. We are actively introducing Graviton 4 into our fleet and leveraging these larger instance sizes, like 96 CPU cores, so that we can bin pack even further and reduce the flattened Kubernetes cluster sizes, because by reducing that, we automatically gain whatever CPUs are used by the daemon sets and system processes. And on top of it, Graviton 4's performance gains will be an icing on the cake. And secondly, as you have seen in the realizing gains section, we had to slowly but surely reduce the resource requested, but it's a very toily process because we have to go make changes to the YAML configurations and deploy the changes. So we wanted to kind of make this process much more seamless. So we are trying to adopt dynamic resource allocation for our workloads by administratively setting these configurations through historical data. And lastly, we are kind of profiling certain workloads where they have sharp spikes during their startup, even on x86, to kind of see how we can further enhance the efficiency of the workloads. Yep. So that's it. I want to extend thanks to the broader Robinhood team that has worked on this project and made this possible. Yeah. I'm going to pass it back to Sudhir.
Yeah, thank you, Sujit, for those wonderful insights, and it's been great to see what Robinhood has been able to do with Graviton. So just a couple more things that I wanted to cover today. As we transition to Graviton, and this is one of the most common questions that we get from a lot of customers is, how does the software ecosystem for ARM look like? And what are some of the best practices that we can follow as we move to Graviton? So I want to start with software first. In terms of operating systems, there is broad support across the Linux community for ARM64 and Graviton. So this includes pretty much all the popular commercial Linux offerings from Amazon Linux, Red Hat Enterprise Linux, or Ubuntu, or SUSE Linux Enterprise Server. And there's also broad support in the community armies for Linux as well on ARM64. Just like Robinhood, we see a lot of customers run containerized workloads on Graviton, so this is super popular. So overall, the support for containers is pretty strong for Graviton on ARM64. So this includes Docker itself. This also includes our managed services like Amazon ECS and EKS. In terms of image registries, there is support for multi-architecture support for both x86 and ARM64. So that makes it easy for you to deploy the right image based on the host type. That exists between both Amazon ECR, the Elastic Container Registry, Docker Hub, and more. So Graviton Ready Partners, so this is a program that we've had over the last couple of years. And the goal really has been for many software providers, ISVs, to be able to validate their software offerings, their applications on Graviton, and make that available and make that discoverable really easily. So these providers run quality assurance tests on their software. They make sure that it's ready and ready to go for customers to use it on Graviton. And that allows customers to discover these sooner and get on the journey of realizing price performance benefits sooner as well. And this includes software across multiple categories, right? So be it DevOps, CI/CD, logging, monitoring, databases, et cetera. So while you can always take advantage of Graviton and EC2 on your own managed service, we also have extended the benefits to the various AWS managed services. So this, in many cases, it helps customers move to Graviton and realize the benefits without a lot of heavy lifting, right? So in most cases, it's essentially just quick instance type change. The managed service handles the architecture compatibilities for you. And for many of these managed services, today, Graviton is even the default option. So this encompasses all the popular AWS services across compute, databases, as well as analytics and machine learning. So some general guidelines. Overall, we tell customers, the more current your software stack, the better it is. As you start moving to Graviton, it just provides you with a better starting point. Interpreted bytecode compiled languages are typically easy to run. They run without modification. If you do have a compiled application, no problem, though you have to recompile it for ARM64, every popular major compiler today supports that. And we have a lot of customers who have successfully deployed C++, Golang, and other compiled languages on Graviton as well. In terms of resources, my favorite link is the first one, which is our Graviton technical guide. So this is available on GitHub, and we've provided detailed resources and guidelines in terms of how you can get started, what kind of tuning you need on the platform, what are the special settings you need for every single application. So for the vast majority of languages and applications, we have that covered on the technical guide. We also have a program called the Graviton Fast Start program. That allows you and provides you with a step-by-step guidance on whether you're starting Graviton running on EC2 or via managed services. There are a lot of good steps in terms of how to get started over there. Couple more things, Porting Advisor, that's another tool that's available on GitHub, which essentially scans your source code for any dependencies that you need and can typically be a good starting point in your overall journey. And we also have this tool called APerf. So as you run on Graviton, as you want to get into performance and troubleshooting performance, APerf provides you with a way to collect a number of performance metrics in one go. So that also accelerates your overall performance troubleshooting journey. So that brings us to the summary of the session. So overall, it's Graviton-based instances are available for a wide variety of workloads, enabling the best price performance and the best energy efficiency. and a lot of great technical resources are available there on that GitHub link. So with that, I just wanted to thank you for taking the time out from your busy schedules to attend our session. We really, really appreciate it. And I hope you continue to have a great reInvent. And thank you so much for your time. And please do fill out the survey in the mobile app if you can. So we'd really appreciate that as well. Thank you.